All right, my clock says 11 o'clock, so I'm going to kick things off here. Morning, everyone. My name is Yves Matson. I am Director of Business Development here at Integrated Sustainability, and I'll be your MC today. I'm sure a few more people will chime in here as the minutes go by, so there's a bit of housekeeping to do here. I'm going to start today's program off here with a land acknowledgement. In the spirit of respect, reciprocity, and truth, we honor and acknowledge this land, Okisis, and the traditional Treaty 7 territory, along with the oral practices of the Blackfoot Confederacy, the Stoney Nakoda, the Tsuut'ina Nations. We acknowledge that this territory is also home to the Métis Nation of Alberta, Region 3. We also acknowledge that our Vancouver office is situated on the unceded territories of the Coast Salish people, consisting of the Musqueam, Squamish, and Tsleil-Waututh nations. Finally, we acknowledge all nations, Indigenous and non, who live, work, and play on these lands and who honor and celebrate these territories. A little bit of housekeeping as you read the agenda today, mostly regarding the questions and answers that inevitably we're asking for and pop up during these. If we have a moderator who'll be going through them, aggregating them a little bit, if we don't get to your question, if we have a good volume of them, then we will be putting out an FAQ to answer them after the fact. The other side is if the question is deemed very, very technical. And so this is more of a general overview of the water situation, the water life cycle through the hydrogen process. So it's really technical, and it probably applies to only a few people in attendance. We'll follow up with you on that question and dive a bit deeper into that particular issue. This slide is here. I mean, if anyone's in the room who doesn't believe that hydrogen is going to be part of the mix, then I'd be surprised. The question is, how big is hydrogen going to be? How fast is it going to come? We all believe in this room that you either decarbonize before you burn it or you decarbonize after you burn it, and hydrogen will play a role in the former. What will be the barriers to hydrogen projects in Canada moving forward is the big question. Obviously, financing is in the room and regulatory considerations in the room, but we also believe that water is in the room in terms of what will cause different projects to be more competitive, different projects to get more pushback as they move through their cycles, and also which projects potentially get public pushback in terms of their footprint and what their benefits are. I'm flashing these key takeaways here to kind of frame the webinars. I'll be displaying this at the end as well. I mean, the key takeaways are water is a trickier critical path element than a lot of the projects that we've been interacting with believe. So most of the hydrogen projects I've chatted with say, well, we'll deal with that when we get to feed. We'll do process optimization when we get to feed. And our opinion is that it should be in fees. Before you go to the regulator, before you go to get that final investment decision wrapped up, water needs to be something that is squared away. And this is true of a lot of industrial projects, not just hydrogen, but certainly in the oil and gas sector and the mining sector, water is now a very, very critical path. I know in some of our mining projects, you deal with water first. You don't deal with it later on. You get your essays done and you determine how much resources you have, and then you figure out water, and everything else comes after that. That's because there's a lot of pushback from various stakeholders. And so that'll be a theme that you'll see throughout this is do water holistically and do it earlier, not just what your vendor says you need for your feedstock. So these are the 5 buckets that we really want to speak to today. Water sourcing is going to be something that you're probably already thinking about. Yes, I do have water nearby, or I've got an ocean nearby, or whatever the case is. You're thinking, my vendor has said I need X amount of water at X spec to go into my process, and that's certainly true. There are some options around water treatment for purity. Certainly, it's probably a reverse osmosis or RO discussion. But RO is itself a little complex in terms of what we call reject water. So it doesn't, not all the water you put into the front comes into your process. How many passes through the RO do you push that reject water? What kind of wastewater does it generate in the back end? Water cooling strategies is a bucket here that I think a lot of people don't pay much attention to in the early process development stage of hydrogen projects. At least that's what I've found. So the water cooling strategies are definitely at the forefront. but they consume a lot more water than the process. And so can we make those other less potable, less high quality waters? The wastewater management side is also somewhat passed over. If you have ample disposal for an RO reject or a blowdown water from your cooling towers, then you're probably in a good position. But if you don't, because geologically you are in the shield, or you don't have access to disposal because the aquifers are already over pressured by, say, oil and gas activities, then you'll have to come up with other options to deal with it. And then the last bucket here, what we'll speak to is the regulatory rights holder and stakeholder impacts in terms of we've seen projects get canceled, and I'll come up with I'll speak to an example of that where everything seemed to work economically, everything worked environmental assessment wise, the technology was well understood, but the pushback from the public who did not understand what the impacts to water were going to be was serious and canceled the project. The surface water use in Canada is not equal in terms of its geography. There are places in Canada, denoted by the red, where water is already very stressed. In Alberta, for instance, there's a lot of closed basins where no new licenses are being permitted. There is the ability to buy those licenses. The challenge is, how close are they to your operations? How available are they? What volume do they have? How reliable are they? So even if you have a license, licenses can get shut down if there is a drought condition. And you guys are going to have these facilities here for 20, 25 years, maybe 35 years. And inside those decades, there will be drought conditions. And so having understood that, hey, I've got water nearby is kind of step A. Step B is what happens if that gets turned off? How do I come up with plan B and maybe even plan C? And can I reach into alternate sources in times of need? And what are those? And how can I store them? And what volume are they at? So one of the things that we have recommended clients in a host of different industries is, what is your storage need? So you might have ample surface water during a portion of the year, but if the freshet falls off and those water resources fall off with it, or in a drought condition, it's only available during a certain portion of the year. Surface storage may be a way to buffer those shortages. So building large reservoirs is understood and a well-established process that many different industries pursue. And so hydrogen will likely need to have this as somewhat of a backup. And it can also potentially play into some of the cooling strategies as well, although depending on what kind of water you're using and putting into there. The North Saskatchewan is a good case study, probably for a few of the projects in the room here, because there are a lot of steam methane reformation projects that are progressing in the industrial heartland. Some new studies have found more water in that basin, and it is deemed that there is sufficient water for a project or two projects. The question is, there's about 4 or 5 trying to progress. And so is there room for 4 or 5 projects is a big question. Probably not. And certainly which project moves forward will probably be one that uses less water and has less pushback in that respect. This is the hydrological curve of the North Saskatchewan. So this is that peak and ebb that I talked about that may require that storage capacity to get through drought conditions and or much lower. One thing that the North Sask will very likely require is analysis of alternative sources. So there are lots of municipal effluents. There's lots of other places for stuff like saline groundwater to enter into the equation. And before they allow a big new straw and huge withdrawals, they will want that analysis put. Is that feasible or not? It's not to say that it will be absolutely required. Quite often in instances, you can demonstrate that it is just not feasible to do that, and that's accepted, but you will have to do that analysis. The other side of it is there is very likely to be a multi-user aspect to that resource. So you won't be able to simply say, well, my project needs a new straw in the river and I need this much water. You'll have to band together in a utility intake on that river. We also get questions about seawater from our customers, predominantly in the Maritimes of Canada. So they would like to know, well, what's the impact? I mean, there's obviously abundant seawater for their project ad infinitum. So what's the impact of seawater on use? And the answer is it's very doable, but it adds a lot of cost, as you might expect. A lot of the projects are saying, well, can I use seawater for cooling requirements only? And the answer is yes, but it does add cost. So that by far the cheapest is surface potable water at scale. It's where that's not available, or the socioeconomic, the social feedback, or the pushback from the regulators and the stakeholders pushes projects to look for alternatives to freshwater and potentially bring in seawater. There are issues in terms of biologicals and sometimes algae blooms. These are the things that other desalination projects have encountered around the world. But the good news is it's very understood. Groundwater is another question. There are strained groundwater aquifers, and there are groundwater aquifers that have high volumes available. The reaction to using fresh groundwater is pretty similar to the reaction to using fresh surface. It's a precious resource that's being used for agriculture in cities and towns. Saline groundwater is another question, very similar to seawater. It varies enormously in salinity, depending on how deep it is, and the aquifers. It can range from slightly saline, 10,000 TDS, all the way up to extremely salty, 3, 4, 5 times more salty than seawater even. But the management of it is very similar. So the kinds of materials required, the complexity of treatment. It is unlikely that you would want to use this for your ultra demineralized pure water for your feedstock for your process, but quite likely that you might turn to it for the much higher volumes for cooling. I spoke a bit about effluent before. Integrated actually has some experience moving, for instance, pulp and paper effluent, millions and millions of meters cubes per year of effluent getting discharged back into a river that's considered engineered water that could be moved to a hydrogen project and used quite feasibly with a little bit of pre-treatment for things like biologicals. But one of the issues in the room when using something like industrial effluent is that it is very likely that plant will have shutdowns / turnarounds to do maintenance. And so what is the risk mitigation around that? They may have an emergency shutdown if something goes wrong in terms of part of their process. And so storing some water to buffer those is probably very likely. Alternative sources that you can kick in if and when that happens. Certainly you try and manage this when, best case, they do it during the freshet and there's more surface water available. One theme we're seeing is that projects that are making use of existing infrastructure, existing licenses for water, certainly seem to have a competitive advantage in this space. So one example is one in Newfoundland that is based very close to a pulp and paper mill that is no longer operational, and it has a large water license that can be appropriated. It has a large holding pond that can be used for that buffering I talked about. So our lens is these projects do have a clear advantage in terms of understanding their water landscape, and they've inherited that essentially from the previous project. What we would counsel is get to as close to that as you can in terms of planning. So while these customers have that infrastructure already in ground and the permits are already in hand, you can move substantially closer to this scenario than most projects we're seeing right now in terms of water, which, they kind of wave the hand and say, we'll figure that out later in detail. For relatively small dollars, you can move the project to a point where it is nearly as well understood from a cost perspective, from an infrastructure perspective, from a permitting and stakeholder perspective, as these already fairly well established water infrastructure requirements for these projects. Regulatory is something I'll return to again in the facility side here, but in terms of water, there is a lot of due diligence required, not just from the perspective of environmental impact and basin impact studies, but also from that stakeholder. Managing stakeholder concerns is really inside this, because there will be periods of consultation. And if you drop a giant water number on them, and by giant, it doesn't need to be in the 20, 30 million cubes here. Depending on where you are, there's already extreme sensitivity to water withdrawals. the oil and gas and to a lesser extent the mining industries have faced this for a long time. And so when you put the notices out and the stakeholder feedback or rights holder feedback period emerges, you want to make sure that you've got this really well addressed holistically, not just from this is how much I'm going to take, but this is what my wastewater is going to look like, and here's what I'm going to do with it as well. And I think part of this is that next phase approach too. A lot of projects are going to start with purely surface water, potable surface water, and then potentially in phase 2, as they plan to ramp up into higher and higher production, what a lot of stakeholder sensitivity comes around as well. Your current phase is doable, but you're probably going to double your production as time goes by. Because that's certainly what you've told the investors. And that's what the investors want to see over time, is that kind of growth. So is your water use going to go up exactly in the same lockstep? And that's got me disturbed, because you're going to be here for 30 years using that volume of water. And so one of the things we would counsel is look at phase 1 as, yes, we're going to use fresh water because we have to get this economically off the ground. But phase 2, we might make twice as much hydrogen with the same amount of potable water and substitute out some of the potable water going to cooling to push that solely into process, and then make use of non-potable sources to achieve the cooling requirements. I think it's also important to mention that regulatory permitting crosses a lot of boundaries, both federal, provincial, depending on where you're locating this project. If you're going to be on the coast and you're going to be interacting with the ocean, there's fisheries and other regulatory bodies to account. So there's a regulatory Gordian knot, as you might expect with projects, especially in Canada. But whatever jurisdiction you're in, you will find yourself with a in need of a very good regulatory roadmap and what the timelines are, because some of these things require a year's worth of environmental studies to determine impacts. And so that this is something we've experienced in depth in the oil and gas industry, for instance. The water demand. I think this slide is really here to speak to the cooling side of it. I mean, when your vendor says I need X amount, be it, let's say 4 to 5 liters per kilogram of hydrogen, or I need 9 or 10 liters per kilogram of hydrogen over in electrolysis. I mean, obviously you're going to put your hand up and say, well, mine's not quite that. Mine's different. Mine's over here or mine's over there. And that's fine. Those can vary depending on the technology. What we do also want to speak to is a representative number here on the cooling side. So evaporative cooling is definitely the most cost-effective way to keep your processes within their temperature bands. But interestingly, the vendor of those gears, I mean, that's really not part of their wheelhouse. They will say you need this amount of water at this spec going in, and you need to keep your process at this temperature. And that's really the job of an EPC or systems integrator, what do you want to call it, to do the balance of plant. And they will take that spec and they will put in the best, most effective, most efficient cooling towers, or whatever the technology chosen is to achieve that. And that's where the lion's share of water is going to get used. Likely in this. I mean, there is the possibility of using air cooled, but it has its own challenges, and certainly with respect to CapEx. So this is a slide to say, that 4.5 or that 9 going in is not the full story of what you're pulling out of that lake or that river because of the RO reject. So there, that number will double, or maybe not quite double, depending on how many passes to the RO you're going to go. But that's not the final number of what you're going to be pulling out per kilogram of hydrogen. And also this number over here is going to have its own associated treatment costs to get that water so it doesn't mess up your cooling system. And it will have its own blowdown water challenges as well with regards to treatment. So that total number is a little more complex than the multiplying the kilograms or tons of hydrogen you're going to make by a certain factor that has been established as a need for your process. This is a pretty standard production process that probably doesn't contain any real surprises for anyone. It kind of reiterates those numbers in there. But this liquid disposal up here, a brine concentrate coming out of the reverse osmosis, as well as there's going to be a liquid waste coming out of a bit of pre-treatment. And so you can see there's blowdown water. There's going to be a liquid disposal requirement here that that various jurisdictions will easily deal with, and various jurisdictions will have challenges with and need to reduce those volumes. When we come to an industrial water use situation, we're always trying to figure out how to optimize it. Sometimes this is, phase 2 optimization, but certainly there are new technologies out there that will lower your cooling requirements, or hybrid cooling between liquid and air cooling, or there's companies out there that will install glycol loops to pull heat out of a system for Rankine cycles to generate electricity. And so there are options out there. Most of the time they add cost, and that's been the big challenge. You won't go to your EPC and say, give me an expensive option here and destroy my economics. You'll say, give me the most cost-effective solution. But that cost-effective solution comes sometimes with water challenges. And so we have some technologies, and I'll speak to those on another slide here, but we have some technologies that help produce more desalinated water, or distilled water, and reduce the amount of liquid waste that has to be dealt with. And sometimes also there is some unforeseen sludge that's coming out of some of these processes that needs to be accounted for as well. So when we look at treatment options for hydrogen studies, it's a very holistic picture that needs to be analyzed, and a lot of cost benefit needs to be traded off in terms of risks, in terms of costs, in terms of geographies, including geologies. Believe it or not, you think you're a pet chem facility at surface, but that wastewater management is certainly an issue. So it's a very holistic look at water that you really don't want to leave till later, because it may include some surprises that increase costs markedly. So it is those technologies I mentioned earlier, I'll speak to briefly, and we can certainly speak to you individually if any of these are of real interest. Thermal systems. I mean, certainly the oil and gas space has had a mountain of brine water to deal with, and sometimes distilling that with waste heat is an option for them, depending on chemistries and so on. Heat exchangers, again, I spoke to this. There are some companies that are doing heat exchangers to make electricity, and are benefiting from that. Could your project generate zero carbon electricity as a benefit? And then on the RO side, there are pressure recovery technologies to get. So you're going to be spending electricity to pump water through membranes at quite high pressures, and when that cycle ends, quite often that pressure is lost as the cycle resets. Well, there are technologies to save that pressure and lower your energy costs. I mean, back to the point I made before, this is a mystical piece of the equation. And the more you think of it holistically as a system, as a part of your plant, the same way you're looking at the power production from various processes, or your feedstocks like methanes, or your takeaways, who's going to be taking your product and how are you getting it to market. This is another piece of that holistic approach to the process that in our lens is more critical than folks give it credit for. In terms of the plant, the regulatory strategy is going to be fairly straightforward. Our view is that the regulators will look more favorably. They don't want political or stakeholder backlash as much as you do, or as much as a provincial or federal politician does. They are looking for plants that use less, that are less burden, have smaller footprints, all those kinds of things. Certainly that's the case in other industries, and we see no reason why hydrogen wouldn't. And another elephant in the room for certain jurisdictions, for instance, in Alberta, is the SAGD world eventually had to use non-potable sources for new licenses. So it was allowed to use fresh water for many years as the industry spooled up, but eventually new licenses, Jocelyn too had to use non-potable sources, aka saline sources, or it wasn't going to get licensed for use. So that may be a precedent that's been set and may occur in this space as well down the line. Certainly probably not at the start, but certainly a possibility down the line. So I'm back to those key takeaways before I introduce our panel. Our lens is that this is a critical path factor. and it is something that should be thought of in the fees aspect of the process project development. It's relatively low cost to move through these and have a much better understanding. And that much better understanding and much better scoped out is gold in the stakeholder engagement portion of the process later on. But I think it's also critical when you're talking to the investors. Investors are increasingly getting very versed in climate change risks. The SEC is coming out with guidelines where publicly traded companies have to analyze the risk of climate change in terms of their companies. So you can bet that large scale investors that are looking at these are going to have an eye on this. And so long before you think you're going to have to answer those questions, you'll be asked uncomfortable ones, and the last thing you want to say is, I don't know, or we will figure that out later on. So for the low costs it costs to figure these out and get class 5 or class 4 estimates on what things cost and what the OPEX looks like and how you're going to manage the intakes and outtakes, small dollars equal a very competent answer when risks to the project over the 20, 30 years are, for your water supply, one of your critical feedstocks, is already addressed. So with that, I will end my presentation here, and I will introduce our panel. Jennifer Katurikis is our VP of Sustainability, Science and Consulting. So she has kind of overall responsibility for the consulting side of this. And when customers say, where can I get my water? The consultants answer that. And how do I get permission to use this? And all those kinds of initial questions in terms of water resources, her team would answer in collusion with Ian Grant, who is our water resources specialist. So he really looks at hydrogeology and hydrology, and he answers the tough questions about where the water is located, how much is it, and what's the process for validating that. And Mohammed Awa is our reverse osmosis expert, our water treatment expert. So he has had extensive experience with desalination plants, massive desalination plants in the Middle East. He really brings the right scale to the table. And he's also done process development for other hydrogen projects as well. So with that, I will turn the mic over to Adam Leese, who has been our curator for the questions that have come in, and he will ask the panel our questions, and we'll go from there. Take it away, Adam.
Perfect. Thanks, Yves. Yeah, a couple questions trickling in. I'll just out to the crowd there. Just throw your questions into the chat if you have any. And again, we'll collate them and try to organize them a bit more and ask some pointed questions here. So one question here comes back on the over to Mo here. We've got a question about the ocean water systems and a question about the energy recovery system. Can you kind of maybe expand on that a little bit? With regards to the saline water, how does that energy recovery system work? And maybe describe a little more about how that functions and what's the value of it.
Sure thing. Thanks, Adam. So energy recovery system basically came like I would say in the last decade, and it kind of changed the whole the way seawater reverse osmosis looks like. So in the beginning, when it came, we were talking about thermal as the only way to desalinate. RO came into the picture. It was still not very competitive in terms of a kilowatt hour per cubic meter of water produced. It was 10 or above for the thermal, and RO was just at 7 kilowatts hour per cubic meter from seawater source. When energy recovery systems came into the picture, and I'll shortly speak to that, the picture completely changed, and now we started talking about 3 to 4 kilowatt hour per cubic meter. So it's a major advancement, technological advancement that reduced the capex, OPEX, and capex sometimes drastically. Now, why do we need them? Obviously, to desalinate seawater, seawater has a very high percentage of salts. And what that does is it requires a very high osmotic pressure, to overcome in order to produce water in an RO system. So, With that, you had to basically increase pressures to the north of sometimes 60 or 70 bars, believe it or not. And that energy is going to go on the back end of the RO process in the reject stream with probably a couple of bars of pressure losses through the membrane. And now you have to break that pressure down to zero and then not make any use of this. So somebody came back and said, well, why don't we utilize this and try to recover that pressure? So the best technology out there is called pressure exchangers, pretty much self-explanatory. So it's basically you take the pressure of that stream, pass it into the energy recovery device that is called pressure exchanger, for example. It's not the only one out there, but it's the best one. And then what that does, you basically put the part of the RO feed on the other side, and it pressurizes the feed to wherever you want it to be, and basically recovers almost, I'd say, 90 to 95% of that pressure energy that's leaving the system. So you can imagine how good of an add-on is that to your overall system. There's multiple other technologies, such as Pilton wheels, for example, such as the weirs, such as turbochargers, which is the least efficient, but the more simple one to implement. And basically, all of them, you have to basically study them separately on a project-specific basis to make sure that you're tapping into the right one and that you're using the right technology for the project. One last question, why do we need them? The major driver for them is, unfortunately, reverse osmosis systems of seawater systems operates inherently at a low recovery. That's around 40 to 45%, meaning, for those who doesn't know, my apologies if you already do, you probably already do. It's basically it's a ratio from dividing the permeate that you produce, the good water, divided by the feed flow. So the ratio of the two is called recovery, and it's quite low in seawater systems. And that means you're generating a lot of waste. That means your pretreatment is huge. That means a lot of things. And utilizing that energy from that big or massive reject stream is basically the goal of implementing an energy recovery system.
Thanks, Mo, for that. Maybe a bit of a follow-up here that's related that we received. So you kind of touched on the CapEx and OpEx of a system like this, but maybe can you maybe highlight some of the key factors that affect those, operating costs, capital costs of an ultra pure water plant? That's obviously that feedstock into the electrolyzer type system, or even obviously into other opportunities
Sure.
in the hydrogen space.
Yeah, sure thing. So the water users in a hydrogen plant are basically two major water users, as Eve mentioned in the past slides. So you have the ultra pure water needs, and by ultra pure we mean very high purity water to the north of 10 mega ohms. And that's how we measure very low conductivity waters. The resistivity measured in mega ohms is basically nothing but the reciprocal of the conductivity. So this is the major one. This is the ultra pure part. This is the complex part. And then you have your cooling demands. And most of the time, this ends up being a very simple treatment system to deal with. It's usually filtration suffice for cooling water pre-treatment. But on the other side, the blowdown or the wastewater generated from those systems is quite challenging to address and to treat, and will add a lot of cost to do so. So first one we already talked about was recovery. So the amount of efficiency, so let's call the efficiency of your system. How much water you're producing per cubic meter of feed? That is the major one. How does that impact your CapEx? Basically, operating at lower recovery when you have your demand fixed means nothing but increasing your raw water demand, right? Because it's the ratio of the two. And when you do so, you basically end up amplifying the size of your pre-treatment system. And that's how recovery basically ends up end up leading to massive investments in capex when you operate at low recoveries. The second one is called flux, and by that mean the production rate of membranes, for example. So production rate of membranes, there is a range, obviously, and believe it or not, when you operate at the higher end of the range, not the conservative one, you end up having better performance. But in certain cases, and that's the third point, the quality of the water forces you really to operate at lower recoveries and lower fluxes, amplifying the size of your system. So water quality, salinity is the major quality factors that really leads to increasing your capex. And as well as OPEX, as I will discuss. So it will add complexity. It will make your materials, for example, in seawater system, it will force you to go to exotic materials such as super duplex stainless steels. A certain grade of those super duplex will only work sometimes. Hastelloy materials for instruments and stuff like that. And pressures, obviously. So when you have saline water, because salinity is high, you'll end up pressurizing the system. So just to give you an imagination, you could be running the system at 10 bars for fresh water, but you could be running the system at 70 bars at saline water. So that's 7 times the pressure and 7 times the energy and many times the size of treatment. The other one is the cooling water demand. That's more simple. And what makes it really very expensive is concentration cycles that you operate with. The lower they are, the bigger your system is, the higher your waste volume is. And that obviously, links back to your OPEX. Most of the same factors we discussed affects the OPEX as well. So when you have a bigger pretreatment, you'll spend more chemicals to pretreat. You'll generate more waste when you have a lower recovery, so that you have to deal with, and you have to consider discharge costs. And same for membrane replacements. Going to be tough if the water has a high scale potential. That's going to require more chemicals to pretreat. Pressures, we talked about it, and yeah. So that's basically how how the various factors plays, and you can see they affect one another as well. So
thanks, Mo. Just to jump in and ask you to elaborate. Obviously, the RO discharge or waste stream is a OPEX consideration, but from an environmental perspective, what are your considerations within that, and what are our options for disposal?
okay, so first of all, you have to imagine that RO is basically concentrating the contaminants in the feed. And that concentration factor is a function of the recovery. So the higher the recovery, example, if you operate the system at 90% recovery, whatever you feed the system from the raw water end will be concentrated 10 times. If you operate at 50, 2 times, and so back and so forth. What people usually do in most of the cases is basically consider sewer discharge if the bylaw limits of that certain jurisdiction allows for it. That's the more simple way to deal with it. It's the more cost-effective way. You'll basically, as Yves showed in the presentation, it's this first slide that we considered liquid discharge. It's that one. So you basically try as much as possible to go in that direction if that's possible. Any other direction is going to be a more complex route. So you could probably, first of all, consider reducing the waste volume by tapping into innovative or more complex technologies. Then maybe consider, hauling to a landfill if you go with a crystallization or zero liquid discharge route. So it really depends on what's the endpoint look like, and eventually you'll have to deal with it accordingly. So
thanks.
Thanks, and it's definitely it's something that the regulator, whatever jurisdiction that you're in, is going to be asking lots of questions around, right?
Definitely.
Great, thanks. Yeah, Mo, great. Thanks for that. Jen, maybe kind of dovetailing off on the regulatory side, you've said had mentioned, what we've seen in other industries is that increase efficiency, water reuse, water recycling, stuff like that. How do you see that sort of being implemented? How do you what's your crystal ball on that front, knowing that ours is what your crystal ball may see in that one?
Yeah, thanks, Adam. I think, like Eve said, we have the precedent that's been set with the SAGD facilities needing to reach that recycling requirement, really driven by water conservation policy and stakeholder concerns and really societal priority placed on water. I think that's not lessening. Water is becoming more and more important across, all of Canada, all of North America, the world. I think it just depends on what's driving it, right? Whether it's regulation or government policy, or whether it's your stakeholders, or whether it's water restrictions or water security concerns. I don't think it's going to lessen. I think it's going to become more important, and I think it's going to be a deciding factor in the success of your project. So it's something absolutely to consider. Like Mo mentioned, there's technologies that are available in order to meet certain thresholds. It's just evaluating your options and evaluating the cost associated with each of them.
Awesome.
Yeah, if I could chime in there too. I mean, I made that point, but these facilities are going to be in operation for 20 or 30 years. And so when Jennifer says, going to be more so, I mean, we're starting to see more frequent basin closures. We're starting to see pressures already. And so if we project forward 20 or 30 years, there's, the investors are going to ask those questions. The investors are not concerned with the first 5 or 10 years. The investors are going to see a return on investment for 20 or 30 years. And so if you can't at least address it and say, well, we have plan A and we have plan B and we have plan C in terms of how to use less water or how to make more hydrogen with the same amount of water, those kinds of questions, they will see risk. And that will imperil a project that probably has several Bs behind it in many cases that will need to address that as a critical path feedstock.
Great. Kind of on that same line, I've got another question here about impact assessments and environmental assessments. Knowing we've got probably a broad group here, but can you maybe speak generally about some of those triggers that we've seen through our clients and through these opportunities about impact assessment requirements, other regulatory permits that seem to be either a forefront or a challenge from your experience?
Yeah, I think it's jurisdiction dependent, right? So which province you're in, it varies across the country. There's a couple provinces that have specific triggers for hydrogen production facilities that just naturally trigger a environmental assessment or an EIA. Alberta and BC specifically, it's more linked to the associated activities that are going along with a hydrogen facility, whether it's a water diversion limit, a water storage limit, a power generation trigger. But really, it's evaluating what's the impact that the overall project is having on the environment and the surrounding stakeholders and landscape and water resource. So there's also a federal requirement that needs to be considered, and the federal requirement, similarly, there is no hydrogen trigger. It's more of an associated activities trigger, such as if it's a hydrogen project on a port and the impacts to the port or the impacts to seawater or aquatic life that is a consideration. So it's definitely a factor. It is evolving, and we're going to see movement in that space, I suspect, but there's always the ability for whichever regulatory body you're considering to require an EIA within that space.
I think, our focus has obviously been on Canada in this presentation and in our discussions. That's certainly pertinent to our wheelhouse for oil and gas, for instance. We're also looking at projects in the United States, and they have the same myriad federal and state and county, and they have a whole myriad of regulatory pathways themselves to deal with. And so, does this apply to the United States? Absolutely. They also have a reality on the ground in terms of water, and certainly projects that are in the Colorado River Basin, for instance, are going to be very challenged to get large water licenses to move ahead, just because of the impacts to that basin right now. So all of this applies across North America, whether you are in the Maritimes and you think you're flush with water, or if you're in California, for instance. All these same factors evolve, and in some places extremely, and in other places, more runway, but certainly a business risk over the coming decades.
Yeah, even I think, as climate change, as we experience climate change and impacts to precipitation and snowpack and river flows, it's just compounding, right? So it's going to be more prevalent, and more requirements across evaluating impacts that projects are going to have.
And that's a tie into Ian here. I mean, Ian, you look at this every day, and our customers come back to us when a basin is closed. Is that, I'm probably stealing Adam's next question here. I apologize, Adam, but how are you seeing that impact in day to day, and what's your crystal ball in your role here as a water resources manager?
Yeah, thanks, Steve. And yeah, both of those are likely to get the impacts of regulatory issues, and also with basin closures that affects groundwater and surface water. So just because you have a license doesn't mean that you are going to have access to get that water. We get licenses for different clients all the time, and then the river's just not flowing the way that it did in some years, and therefore in that year they're not allowed to get water. So it's always good to have a backup strategy for water, whether that be a different water source, whether that be a way to store it when the water's there, so that you've got extra so that you can use it at different times, or what have you, right? There's lots of different ways to develop your water reliability for potential changes.
Yeah, actually, it's a good point here, and it kind of leads into another question we've got here, just about the use, or I guess the differing challenges between surface and groundwater here. So touching on the fact that surface water isn't easier maybe to get started, but they have those inherent challenges related to climate change, versus groundwater, where we hear of situations where groundwater depletion is obviously a critical thing here. Can you maybe touch on some of those different challenges, or anything that we haven't touched on at this point?
Yeah, and they both will have their own regulatory challenges, potentially different technical assessment route that you'd go to get your licensing, but they're both going to go through a very similar regulatory path to get those licenses. Groundwater might have, depending on how deep you go, it's going to have a higher total dissolved concentrations as you go deeper. Groundwater is also going to generally have less total suspended solids, so less like primary treatment that you'd need there, versus surface water is going to have potentially some fluctuations in your water quality over the year, potentially some turbidity issues at various points of the year, and it's you'll potentially be able to get more water at certain periods of the year, but versus a groundwater source where you're going to get a smaller rate for a more continuous period of time. So they both have their advantages, they both have their different disadvantages, and it's good to consider both of those things and what your backup options might be.
And if I can speak, Adam, also to the water treatment side of things. So what we see usually in recent years is, due to climate change, there's an increase in the organic content of surface water globally. And that basically makes your pre-treatment and makes your ultra pure water system for hydrogen, makes the design more complex, makes the design become more conservative, hence higher capex, makes the operations more complex because of just that organic constituent. On the other hand, underground water is, yes, it's definitely has lower TSS, but sometimes it's really one location. It's location based. Sometimes you dig one well, it's very good water. You dig a well next to it, then it's contaminated with iron bacteria or manganese or H2S, and that doesn't really work in your favor for the ultra pure water plant. So it's really there's a lot of background work you need to do to really properly define the route. And it's not just saying I'll tap into seawater or I'll tap into groundwater and that will solve it. You need to specifically study that water source and analyze it and see if it's suitable for you or not. I'll just tell you one example from the past. There was a harbor in the city of Abu Dhabi. We were drawing water from one location near to the harbor. We were cleaning the massive RO plant for steel industry. It was cleaned every week. Should have been cleaned every 3 months, believe it or not. And by just simply shifting the source few kilometers away, you don't have to deal with this, waste generated from the port facilities and from the ships, basically, and everything was, so that was obviously too late to do. And this is a perfect example to say, it's just not just saying, I'll go seawater, it will solve the problem. You need to be very specific and see where you want to tap your, feed water from. So,
And that seawater draw is not a panacea either. I was going to mention this project, I think I forgot to, but Acton Gas in the Maritimes was going to drill a large saltwater cavern to store natural gas, and it had its chemistries for water in and then brine wastewater into a marine estuary. And all the experts said that yeah, this is fine, this is no good, this is no problem. Your dilution rate is excellent, all thumbs up. But the stakeholder reaction to, you're going to wreck our river by dumping brine water into it, even though it was an estuarine river, was so fierce and got to be such a bête noire that the project ended up being canceled. So, when we're looking at these projects, there's a technical side, but there's also going to be a political side. There's nothing that isn't political these days, and certainly large mega projects have their fair share of it. You want to get ahead of the technical aspect. You want to get ahead of the risk aspect, and certainly that stakeholder engagement and regulatory engagement is pretty critical to try and avoid those walls popping up. Excellent.
This is actually a question I've just come up with here, and pardon me if it's a little bit off, but we've seen a lot of re-injection type conversations here in certainly some of the oil and gas industry here. Can groundwater be used through a cooling system? Can it be re-injected? Can you use the earth as a thermal sink to get rid of it? Ian, what do you kind of foresee? Are there any potential issues with doing so, or Mo, anybody on the panel here from that perspective here? I mean, more just curious.
Yeah, you're talking about putting your heated water underground, allowing it to cool, and then pulling it back somewhere else. Is that what you're getting at there?
Yeah, you bet.
Yeah, so I mean, that's definitely possible. I think depending on what else is in that water, you have to know that you're going to be influencing the water chemistry outside of just your area. So you're going to have to evaluate what the impacts of that are going to be on, other water users or the larger aquifer unit, whether that's a near surface aquifer that's contributing to human water use or something like that. All of those things would need to be considered there, but that's definitely an option that you could consider. I think whenever you're talking about disposal or injection of water into the ground, there's 3 things to consider. I generally say is one is the geology and what's containing it or what's not containing it. The other is physically the pressure, how much water can you inject, where is it going to come out of, how's that going to move through the subsurface. Potentially you'll get some gain some benefit there because you might get some natural filtration, and then the last one is chemistry. What's the chemistry of the water that's down there, and how's that going to influence the chemistry that you're hoping to pull back up later? I mean, we can always do compatibility studies to evaluate disposal water and what sort of an influence that's going to have on the water that's already down there. Are you going to get additional precipitates on your well that are going to cause you biofouling or some sort of reduction of efficiency of your injection well over time? And part of that might also be, filtration and making sure that you've got everything filtered out of it so you don't have physical blockages or contaminants getting down there that are going to, again, reduce the efficiency of your disposal well over time. So definitely possible, but same with any other groundwater supply or groundwater injection project. You need to, as Mo was mentioning, look at the whole life cycle and the whole picture and understand what's going to happen, not just when you first start doing it, but what's going to change over time.
Yeah, and I can also speak to something here. So, as we said, there's two sources of wastewater in an ultra-pure water plant for green hydrogen. The first one we talked about was the reject of the RO. The second was the blowdown of the cooling water system. Now, the problem is, as we mentioned, probably, roughly there, the reject of the RO, you have to imagine it's running close to, it's actually oversaturated. The only reason why the salts are not precipitating out is the anti-scalant. And as soon as it leaves the system, few probably kilometers away, that anti-scalant effect will go away. And now you're having salts that are overly saturated, probably a couple of 100 times more than saturation. And then you have to think about that when you do these kind of analyses and you look at the discharge. So sometimes it's really challenging. Sometimes, and the other thing is it's not easy once the salts are oversaturated to go back and precipitate. But it happens, especially with ROs, because you're running many folds beyond saturation. So that's another challenge that I can speak to. So.
Yeah, and one of the things that I've seen is projects along the coast are saying, well, we'll discharge into the ocean. And yes, there's a short and quick, that is an option. One of the challenges is you're releasing an ultra dense plume of heavy water into that into there. You're precipitating things out, as Mohammed just said. So the marine outfall is doable, but it's not as simple as I've got an inexhaustible place to put it. There are impacts to the marine environment as well from a heavy, dense plume. You have to do plume dispersion modeling for that, and how close you can be to sensitive near-shore marine environments is heavily weighted. So the costs will increase as the pipe needs to move further out or into less sensitive zones. So they're all doable. Everything is engineerable. It's a question of cost benefit, and one of the key messages of today is. You're going to get questions from knowledgeable people who have been through this analysis of projects multiple times. So they've already done some learnings. Some of these investors and some of these government bodies, and you're looking to for public funds. They've already been bitten a couple of times by some questions they couldn't answer, and they're coming with those questions for you now. How are you going to mitigate risk in 10 or 20 years of not having a feedstock? How are you going to avoid this impact? How are you going to avoid these stakeholder pushbacks? And so the more of that homework you can do up front to show that, A, you're thinking about it, you might not have all the answers yet, but you're thinking about it and you're mitigating and you're getting multiple pathways to not only be able to produce 24/7, but also be able to mitigate risks and impact to the environment.
Yeah, Eve, I was going to jump in there and just along the lines of risk, right? So it's looking at your entire project life cycle and understanding what are the risks associated with your process, what are your risks associated with your water source, what are your risks associated with stakeholders or regulatory timelines, and planning ahead of time as best you can. Things change, right? 15 years, 25 years is a long time. Things will, become full life cycle, and we'll see many changes throughout that time. But really identifying what are the risks that we see now? What do we really high level confidence that we're going to see in the future, and creating a plan and creating an approach to address them.
Excellent. We've got a couple of minutes left here, so I'm conscious of ending on time here. I'm going to use those for a little bit of housekeeping. We'll be collating an FAQ here around these questions. We'll distribute that to everyone who signed up for the webinar. I believe we'll have a recording as well. So we'll have some materials. We're working on a bit of a position paper that's just about ready to get published. So we'll have a few follow-ons to share with you and answer questions. But we also invite you to reach out to me and initiate conversations with any of the panelists or all three. We're always open door here. This is certainly a space that integrated sustainability is well equipped from a multidisciplinary perspective, and that's really why we have these three panelists. We wanted to show the length and breadth. We were created to solve complex water problems from a holistic perspective. That water molecule, as it works its way through the entire process, you're not kind of engaging 4 different firms to answer these questions. We're one throat to choke, per se, for water. So feel free to reach out to us. We'd love to have more conversations with you. I'll finish this up by thanking the panel for their time today, obviously, and thanking all of you for attending today. We really appreciate you spending your time with us, and we look forward to future conversations. Thank you, everybody. We'll sign off now.
Thanks.
Thank you.
Thanks, everyone.